Well, hello everybody, and thank you for joining us today. It's very nice as I look down at the list of participants that many of you are growers that I might have visited your location sometime in the past, whether it's here in the United States or Latin America or Africa. And welcome to today's webinar. And really, I think that when it comes to solving water quality issues, we can learn a lot from other growers. And so because there's so many different kinds of water quality problems that we could be dealing with, I think it's useful to have some specific case studies or stories where a grower's had a specific issue and then has gone about finding a solution. Now, the files that Philip mentioned here, the links that are on the right of your screen, there are 4 case studies, including case studies that I'll be talking about in today's presentation. And the bottom web link, the case study video web link, is from Dr. Rosa Raudales at University of Connecticut, which also goes through another grower water problem. Also, I'd like to recognize our Clean Water 3 grant team and the growers in the Floriculture Research Alliance for helping support this project. So the first thing to think about is when we discuss water quality, we might be talking about a lot of different things. And one of my goals for today's webinar is that you're going to be an informed consumer, an informed decision maker when you're thinking about which technology might apply in your situation. So you need to know what you're treating for. You may have a biological water quality issue. It could be plant pathogens, as was discussed in last week's webinar, algae growing on growing media or the surface of your greenhouse or nursery. It could be biofilm or microbes that are clogging up your irrigation lines. Or it could be something chemical. It might be a pH or alkalinity issue. You might have high electrical conductivity or EC, often from sodium or chloride. But there may be some specific salts. It might be high iron or calcium magnesium, hard water, that might be causing issues. In addition, as we're using agrochemicals that may be running off into our recirculated irrigation water, then agrochemicals can be another type of chemical problem. There are also physical issues that are dealt with filtration. So this would be where we've got particles in our irrigation water. So before you buy an equipment, you want to identify which aspect of water quality you really want to have treated and get your water tested by a lab so that, for example, they may be testing for Pythium phytophthora for a biological problem, they might be testing the salts or an agrochemical for a chemical issue, or they might be doing a total suspended solids measurement for particles in your water. So there are so many options, and this is one of the challenges. And all of these different technologies that we have available for water treatment, they are all good quality solutions for certain problems, but there is no silver bullet. There is no one technology that's going to solve all water quality issues. So there are some things to think about as you interact with vendors or consultants who may be helping you with your water issues. And it's not that I'm suggesting that the technologies are not good. It's just that every technology is only going to solve a specific set of solutions. And it's so much easier to suggest solutions when you don't know too much about the problem. So you really want to look at your irrigation water, the water quality, and not only the technology that might be put in place, but some of the secondary effects of how that's going to work around all the other aspects of your main business, which is producing plants. So for example, you might put in place an ozone or UV treatment system, but a secondary unintended consequence of that may be that it's taking out micronutrient chelates. Now with any vendor, are they selling you a solution looking for a problem, or are they helping you identify your water quality problems and then helping you see which is the specific technology that's going to be most appropriate? And when I visit growers, I'll often see a museum of technologies that have been mothballed, where a vendor has come in and has sold a very good technology to the grower, but it never was maintained properly, or it wasn't dealing with a particular water quality issue that they had, and so it was set aside, and then they wait for another technology to come along. So again, without overemphasizing this important first step, is you need to know what your specific problems and goals are, and also think, how are you going to pay back on the investment in this water treatment technology? It's unlikely that you're going to be able to sell your product for more just based on you having bought a nice shiny piece of water treatment equipment. So you need to know what specific benefits you're going to have in terms of reduced risk for diseases, reduced clogging of emitters, or perhaps less labor associated with grading your plants when you buy this technology. So you need some type of return on investment. Now, there are so many different types of water quality issues that we could be dealing with that we really just have to take some specific examples and go into them in depth. And I'll go through 3 examples of growers dealing with problems related to clogged emitters, agrochemical residues, or filtering of particles that are coming off flood floors. And one of the challenges for growers is we're trained to grow plants, and there are always so many options for water treatment, and it's outside of our typical area of expertise. So here, for example, is a technology on magnetic treatment of irrigation water, which is evidently helping in this Australian study to improve crop yield. You don't really want to be the first adopter of these technologies. Talk with your vendors. Some of this can be very technical, and they can help you with the technical specifications of their technologies, but also talk with other growers. You don't really want to be the first adopter. And so as we go through these 3 cases, we can learn from these 3 growers and the decision-making process that they went through. So our first case is going to be a citrus nursery in Florida where they had blocked drip emitters in their greenhouse. It was a new operation. They were pumping 5,000 gallons per day, and for those of you using metric system, 1 gallon is around 3.8 liters. They were having clogged emitters, which was they would see out in the greenhouse by plants that were wilting, as we can see over on the right-hand image there. They were using a well water source, and one of the features of well water is that typically we're not dealing with plant pathogens being in that well water, but rather we are more likely to have chemical issues. However, sometimes we can see bacteria in well water, particularly if it's a shallow well. The grower was using water-soluble fertilizer, a nutrient solution, and line cleaner. And so this line cleaner was being injected into the lines, and it had an acid and chelating type product in there, but it was not adequate to keep the lines clean and free of clogging. There was a screen filter in place for that well water, and it did not have automatic backflushing, so the grower was having to come out and manually clean out that screen once a day. Now, there's a question that's just come in on the chat box. Is the PowerPoint available to download? No, it isn't, but all of these cases are in the articles in more depth that I'm going to cover in this presentation, and you'll also have the video being archived. So when we're looking at drip emitters or boom emitters that are clogging up, there are several possible causes. One of them is biological. And so if you look at emitters and you look at a slimy, snotty, organic material that's gunking it up, it's probably going to be a mix of bacteria and algae, a biological issue. If it's a chemical issue, it's some type of a salt or a crystal that's forming, or an oxide, then often if we put those emitters into a low pH solution, such as vinegar, and leave them overnight, then we may find that that crystalline material dissolves and cleans up. We can also send some emitters, or the solution that the acid solution that we've used to clean the emitters, off to a nutrient testing lab to see what ions come back. And often it's going to be something like calcium and sulfate and perhaps iron manganese. It can also just be particles where there's not adequate filtration. And with sediments, it's often going to have a gritty feel to the particles that are clogging the emitter. And when we soak the emitters in water and shake it, then solid particles may drop out. Now, if we look at the water quality report from this location, we've got some different places here in the locations within the greenhouse where a water sample has been taken. As we go from left to right, we see the pH, the acidity, we see electrical conductivity, the total dissolved ions, the dissolved iron concentration of parts per million, and then the total suspended solids. These are kind of chemical tests we'll often run when we get a water quality sample into our lab. The pH levels are all moderate. If they're higher pH, it's quite often that we may have associated with that perhaps high calcium, magnesium, and hard water, and perhaps we run into a chemical problem. The electrical conductivity from the well was low. Any value that's below 0.5 is a very pure water source in terms of total dissolved ions. The EC goes up out in the greenhouse because we're adding nutrient solution. The dissolved iron concentration is fairly high, and it's high enough to start to think, well, maybe this could be a cause of our issues. However, there are very few particles, so we couldn't detect any particles, suspended solids, and to do a suspended solid test, what we do is we pass the water through a very fine filter and see what comes out. However, although there weren't suspended solids in the well head, so the bore water immediately coming out, the suspended solids level out in the greenhouse was high, indicating that something was precipitating out in the irrigation system from the well as it went out to the greenhouse. One of the other important things, and we're going to come back to iron, is that this is a test of dissolved iron. And when there is high iron in water, often that iron may initially be dissolved, but it oxidizes over time and forms rust particles that may come out into and cause irrigation emitter blocking. Now, one of the other tests that we do is a biological test, and we do use what we call Petri films, where we take a small sample, a 1 milliliter sample of the irrigation water, and we plot it out into what these look like sticky cards, but they're actually a dehydrated culture medium. And Dustin Metter, who's now working in the Center for Applied Horticulture Research in California, did this work in his PhD. And he found that the counts for aerobic bacteria were very closely related to the risk of biofilm developing. And so what we'll do is we'll count the number of dots, and every one of those dots is a CFU, a colony forming unit. If we get a lot of dots, a lot of bacteria, then that means there's a lot of growth in the irrigation water. A value that is above 5,000 colony forming units per milliliter indicates a high biofilm risk from that irrigation water. As a grower, some growers will use Petri films themselves. It's a product from 3M, but in most cases you can send your water sample into a lab and ask for a aerobic or heterotrophic bacteria count, a total bacteria count. These are not necessarily pathogens. They're probably benign type of bacteria. However, a high bacteria count indicates there is a lot of microbial load in your irrigation water. All of these values, including right from the wellhead, had very high bacteria counts. And those values increased as the water passed from the well out to the greenhouse. So our diagnosis, and what would we do? Well, what we have here is a case of iron bacteria. The iron in the water and initial bacteria in the well are causing a biofilm issue. So the treatment solution in this case was to inject sodium hypochlorite or liquid bleach at 2 parts per million to oxidize the iron and kill the bacteria. The grower installed some sand filters downstream from the chlorine injection so that it would catch the particles that precipitated out as dissolved iron turned into rust particles, and would also take out some of the bacteria that would now be killed. Providing some contact time between the treatment and the filtration of at least 2 minutes is desirable, and in this case the grower had enough distance between the chlorine injection and the filter to be able to get that contact time. Sand filters are particularly good when we've got an iron problem because they're a depth filter, and so the particles get caught through the layers of sand in the filter. Now in this case, the grower was able to get a very rapid payback on their investment. And recalling back with an earlier slide, we said, figure out how are you going to get a return on investment in any water treatment system that you put in place. In this case, we've got very simple technology. We just have a chlorine tank, we've got a chemical injector, and so our fixed costs were around $9,671. The variable cost in this case is sodium hypochlorite. And sodium hypochlorite is one of several types of chlorine. Some other options to provide chlorine include calcium hypochlorite tablets, chlorine gas. There are some concentrated hypochlorous acid products, and also ECA, which is an electrical way of generating chlorine on site. The benefits here, if we look at the value of marketable trees in those greenhouses after the clogging was corrected, was $280,000, whereas they had lost a very large number of plants previously before putting in the water treatment system. So the net gain in year one was $112,000. So the return on investment is pretty straightforward. When you have a water quality problem, it is usually very easy to get a payback on investment because the value of your crop and perhaps the labor associated with roguing out plants and so on very quickly pays for an investment in an appropriate technology. And again, all of these costs where I'm using gallons, then 1 gallon equals 3.8 liters approximately. So here we've got another image of the Petri films with the bacteria count before the treatment at the wellhead. It's 56,700 colony forming units per milliliter. It's very high. And after chlorination and out in the greenhouse with the emitter, then we have no bacteria. So it was a very effective type of treatment. Now there's a question in the chat box here of how do we know that they were iron bacteria? Well, one of the things was that we looked at the water, and this is the backflush water from the filter, and it has that red appearance of iron. If we took that solution and we added acid to it to make it dissolved and we measured iron, we knew that iron levels were very high in this material. So we knew that iron was a problem. We looked at the other aspects of the water test, nutrient water test, and the other aspects of water quality, chemical water quality, were good. We also knew that there was a high bacteria count, and if you looked at the type of slime that was accumulating in the drippers, it had that very typical orange, snotty look to it that's typical of iron bacteria. With manganese problems, often it's a darker, more of a gray or black color. So general biofilm control techniques, whether it's from iron bacteria or other bacteria, are to go through the following steps. First, if you have a biofilm problem, you need to clean out your irrigation lines. And that can be very challenging because you're going to go on with a high rate of a sanitizing solution or line cleaner. One of the common brands, for example, used here in the United States is Strip It. You're going to power wash that solution and blast out whatever mess there can be that you can. And often you'll do that. You'll add in the chemical, leave it for 1 hour or overnight, and then blast out that material. A sanitizing shock can be applied where you can use an oxidizer such as chlorine dioxide, chlorine, or peroxyacetic acid and leave that for a period of hours. And again, blast out that material. Now there's going to be a lot of organic material that comes out, and in addition there can be some residues of chemicals that are definitely going to burn the plants. If you're cleaning out hanging basket lines, you want to make sure there's no dripping going down to crops underneath, for example. So without cleaning out those lines, if you've got an existing biofilm issue, then you can't put on a sanitizing agent such as chlorine dioxide, chlorine, or peroxyacetic acid at a low concentration and have them work. Because what will happen is there will be continual sloughing off of this biofilm, and it can actually be even worse than putting no sanitizer on at all. Now, there are a number of different sanitizing chemicals that we use, or treatments that we use. Some of them are very reactive and short-term. They're almost like a point treatment. Other treatments are residual and long-term. They take longer to work. So, for example, if we have a point treatment, it could be filtration, UV light, or filtration. There's no residual effect. Ozone is a very reactive material. Then we go chlorine and chlorine dioxide and chlorine. As we go up the table here, then we have slower acting materials. So, for example, UV and ozone will have a very effective initial treatment against bacteria, but they're not going to travel down the irrigation line as long as some of these slower acting chemicals. Probably the ideal chemicals for nutrient solutions for biofilm management would be chlorine dioxide. If you're not using water-soluble fertilizer, then chlorine would be also a very good option, as was in our case study. It's also a lower cost option. Copper ionization is a slower acting material, and a lot of the activity of copper ionization will actually be after the water leaves your irrigation line and is being applied out on the crop. So, for example, copper ionization is very effective as a way of suppressing algae on the surfaces of seedling plug trays. So when we're dealing with biofilm control, usually we're dealing with chemicals that are in the middle of this table. We've also recently set up, as part of the Clean Water 3 research project, I've got students Andrea Neira, Jasenia Mosqueda, and Ulrich Adegbola, who are all working on a system now. It's based on a system that was developed by Peter Conjoyan at Massachusetts, where we've got fertilizer coming in and then application of different sanitizing chemicals, and then we look at biofilm measurement in terms of these viewing clear lines as well as effect on flow rate through drippers. So another type of water quality issue is in terms of chemical residues, agrochemicals. So in this case, we have a recirculating irrigation system where there are plant growth regulators that are being applied, and Paclobutrazol is the active ingredient in products such as Bonsai or Piccolo, and it has a half-life of 6 months in the water. And that can cause a problem because as that water is recirculated at a low level, even though it's very much diluted, it can have an effect on sensitive species, such as Begonia. So you can see that the control plant with no Paclobutrazol on the right is considerably larger than even 5 parts per billion. And remember, 1 part per billion is the same as 1,000 parts per billion is the same as 1 part per million. So a very, very low concentration is all that's needed to suppress the growth on certain species. So one option would be to use ozone. As I mentioned, it's a very effective oxidizer. And we did some trials in a greenhouse with a large ozone system and filtration system. And what we found was, without treatment, if we added in a Paclobutrazol solution, then we were, depending on the experiment, somewhere between 70 and about 130 parts per billion. And as it passed through the ozone, then with each pass it would reduce the concentration of Paclobutrazol by about a half. Another option would be to use granular activated carbon. And so this is where you have some small particles that are around about 1 millimeter in diameter approximately. And we have modified sand filters filled with this granular activated carbon. And here are some technical details about the installation here. They had 3 filters in series. Each filter was 264 gallons or 1,000 liters in size. The flow rate was up to 50 gallons per minute, which is close to 200 liters per minute. And so the maximum contact time was going to be around 3.3 minutes per filter, or 10 minutes per filter in total. And we did some analysis here with my graduate student, George Grant, and we ran some experiments with using different numbers of filters, and also the grower did an excellent job of sending samples into a lab before and after filtration every week over a period of a year. And so here are some of the grower data, and the tan color is before the granular activated carbon filter, and the concentration of Paclobutrazol in parts per billion, and the blue line shows the concentration after the filter. And so you can see that even though the pre-filtration level got all the way up to over 70 parts per billion, then after the granular activated carbon, the maximum level we had was only 3.3 parts per billion. And we're now doing, as part of George Grant's project, he's now looking at other agrochemicals which can also be adsorbed onto the carbon. So the grower had 3 different crop cycles: bedding plants, chrysanthemums, and poinsettias. And you can see that although the concentrations that were being applied, the before GAC filtration concentrations varied, we had very consistent control of the post-filter concentration. And one of the key questions that growers ask is, how often do I need to replace my filter? Which seems to be roughly once a year. So all of the Paclobutrazol concentrations were below our target of 5 parts per billion, which is a target for sensitive species. And with further research work, again with the Clean Water 3 research project by George, he did some research work with a filter system at the University of Florida and also out at the grower location. And again, we very much appreciate the fact that we're working with these great growers who allow us to collect data in their operations. And so here we've got a graph with the percentage of the control in terms of Paclobutrazol concentration. We applied a solution of 50 parts per billion. And then with George's research system, he had increasing contact time as the water passed through 1, 2, 3, 4, 5 filters. And you can see that by the time we get to 24 seconds of contact time here in our research system, then we were able to close to eliminate most of the Paclobutrazol. And if you are a grower and you're concerned about the possibility of chemical residues in your irrigation water, you can send it to a commercial testing lab. In our case, we used a laboratory in Georgia. But you can also do a little bioassay where you apply your irrigation water to begonias in the case of Paclobutrazol, or we also use broccoli seedlings. And you can clearly see, if we compare the control plant with no Paclobutrazol on the right-hand side, we can see very severe stunting in the top left with no filtration, and then increasing plant size as we have increasing filtration. So with our studies that we've done both in the research environment and also in commercial operation, what we would recommend is a 15:1 filter volume to flow rate ratio. So that means if you've got 100 gallons per minute flow rate, you'd have 1,500 gallons of volume of the filter. If you had a 100 liter per minute flow rate, you'd have a 1,500 liter filter. It's worked very well. It's a very simple technology, and relative to the cost of some of the other technologies, such as ozone, then this is a very low cost and low maintenance type of technology. What some growers are now doing is they're using combinations of technologies for chemical removal, such as having a ozone injection followed by the carbon filtration, so they can take out some of the chemical residues with the ozone and polish the water with the carbon filter. Now we're moving to our last case study, which in this case is where we have a grower who has an ebb and flood concrete floor greenhouse range. And it's a very good grower. They in Michigan, they had a lot of experience, and they were adding on a whole new range, several acres or hectares of production. And so they were having to make a decision about what kind of filter to use to take out all of the leaves and soil labels and so on in their irrigation system. So this is really a physical aspect of water quality type of problem. In the case study location, the older range included a vibrating screen filter. And so there's a metal screen which is moving very rapidly back and forth, and it pushes out to the edge all of the particles that are going through. And they also used a paper or fabric filter, and here the water passes through the filter, and as the paper, which filters out the particles, as it gets clogged, the water level rises inside the filter and the paper indexes forward. So the more material, more particles there are in the water, the more quickly you'll go through this disposable paper, and also the finer the pores in that paper, the more quickly it will clog and index forward, increasing cost. Now, Dr. Jinsheng Wang, as part of the Clean Water 3 project, looked at the effectiveness or the efficiency of filters, and one of the main ways we looked at that was to see the total suspended solids, the weight of particles before and after filters. So, for example, in this particular paper or fabric filter, before the filter there was 12 milligrams per liter or parts per million, and after the filter there was 5.9, so it was about a 50% reduction in the amount of particles. And when we looked at lots of different filters, these are all in commercial operations, and we tested the suspended solids before filtration, and this is all recirculated water, and so that's in the red color. That's the suspended solids before filtration, and then the black lines is after filtration. And we've got all these paper or fabric filters from different greenhouses on the left, and we've got different types of screens or metal screens on the right. And so basically what we know is that with each stage of filtration with recirculated water, you take out roughly 50% of the particles. And if we're going to target from EPA recommending less than 5 parts per million of suspended solids, we're going to need multiple filter stages. One of the ways we describe filters is in terms of mesh size or microns, micrometers in terms of diameter. And one of the important things here is that as we go into an increasingly fine filter, then we'll get more rapid clogging, and often we have to go with a lower flow rate. So what is often done is we have multiple filters in series. These physical screen or paper filters are too coarse to filter out zoospores, infective spores of pathogens. For that, we need to have membrane filtration rather than a type of a screen filter to be able to get out the microbes. We can also send a water sample off to the lab here, the engineering lab, and they have different types of equipment to measure particle size. In this case, they're taking a photo of the particles that are in a recirculated irrigation water. And they can analyze the diameter of these particles. And so here we've got a number of different greenhouse locations around the US, and the median particle size, so half the particles were larger and half the particles were smaller than this. And so you can see that somewhere around 140 or so microns was around the median particle size. So that means that with recirculated water, if we're using a 100 mesh screen or 149 microns, we'll take out roughly half the particles with that one pass. The dirtier the water is, the dirtier it's still going to be after filtration, and we may need an additional stage of filtration. So to come back to this paper filter here, one of the things we looked at was what was the micron size on these papers. And what we found was that even though the vendors were describing a certain micron pore size of the paper, in fact, the holes were much bigger than was reported for the paper. And one of the challenges was that the growers would use a coarser paper so it would reduce the amount of cost of the filtration. Rosa Raudalius at the University of Connecticut did an economic analysis, and if we look at the vibrating screen filter, then if we just come down to the bottom line cost here is per 1,000 gallons, because of the only real consumables being electricity, it cost around 16 cents to treat 1,000 gallons. With the Clearstream paper, a lot of the cost was in the paper itself. You see the fabric and the consumables. So the cost was about twice as much for the Clearstream paper. So clearly it would be better to use the vibrating screen cheaper filter as the first stage before we go into a finer paper filter. So the solution then for this new greenhouse range was that the grower put a coarse bow filter and then a finer paper filter in series. So the bow filter took out the large particles, the labels and so on, and then that pre-screened water would then pass through the paper filter. So just to summarize here, we're almost at the end of the presentation. When we're looking at successful filtration and taking particles out of water, we really need to know what type of particle we are filtering for. For example, if we're using a filter to take out iron and manganese, then we might use a sand or green sand type filter, as in our first case study. If we're taking out chemicals, we might use a granular activated carbon filter. If we have pond water, we may be using a sand or a disc filter. So it's important to get a professional design from a company selling more than one type of filter so that they can target the correct type of filter and also the correct micron size. Specifically, some things we can learn from this case study about filtration for flood floors. 2 levels of filtration are ideal. We can go with a simple screen filter with larger pores as the first stage, and then have a second stage, a finer filter that might have a higher operating cost per 1,000 gallons. We want to filter as a first step before sanitation because it'll take out particles such as peat that will use up active ingredient from our sanitizing chemicals. Filters don't work as well in a commercial scale as in the lab because we have high flow rates and high pressure. And often the micron sizes that are reported are really not the effective micron sizes in commercial practice. Screen filters are only going to remove the pathogens and microbes that are embedded in large particles. They're not going to be fine enough to take out the zoospores themselves, for which we need a membrane filter. Self-cleaning is highly desirable to reduce the amount of labor to maintain the filter, and have a plan for what you're going to do with that backflush solution, especially if you're using a nutrient solution. So with that, I'm ready to take any questions. As you can see from this presentation, there are a lot of different aspects of water quality. We want to identify what our goals are, and then by talking with other growers and talking with industry experts and vendors, we can target a good design because things should be made as simple as possible, but not any simpler. Thank you.